All right, so we're going to check out projectile motion, kind of describe it a little bit, then get on into some more technical stuff. Um, we should define what a projectile is first and kind of what it isn't. A projectile is something that's flying through the air, but it's not undergoing any kind of powered flight. So like an airplane, a helicopter, a bird, none of those things are projectiles. It's something that's given an initial kick and then it's left to fly through the air on its own. So like throwing a ball, kicking a rock. Those types of things, shooting a gun, shooting an arrow. Those are all examples of projectiles. One thing that they have in common, no matter how they get kicked or thrown or shot or any of those things, is they all follow the path of a parabola. And so we can get lots of different looks out of these just depending on the complexity of the problem. But we can get something that looks like this. We can get something that looks like this. We can get something with kind of a smaller angle. All of those things are examples of parabolas that a projectile could possibly follow. These types of problems, where they start to get launched at angles, are more difficult than the problems that we'll talk about in this video, where they are just launched horizontally. So in other words, they're thrown perfectly horizontal or shot perfectly horizontal. We'll get to these in the next video. In terms of interpreting and dealing with these angles. But we're going to kind of look at this to start. They're all these parabolas. You look at these problems and they really are like free fall problems. So they're like a chapter 2 kind of problem, like free fall, that have some kind of an initial horizontal velocity. So it's almost like two problems in one. And in fact, if that's the way you look at these, you'll be in good shape, because you want to think about the horizontal and the vertical parts of these completely separate. And so it's kind of a 2-for-1 deal. That's what makes these a little more challenging, is it's got two parts, because we're talking about a two-dimensional motion kind of thing, and you have to evaluate them separately. But if you can get that programmed into your brain, then understanding these will get a lot easier, I think. And the math will definitely be easier that way as well. A couple things just to discuss about these is that we assume that, and I'm going to use this parabola right here because this is what we're going to be talking about, these horizontal projectiles. We assume that when this thing is launched, that the horizontal velocity, so the velocity in this direction, the x direction is another way to say it, is constant throughout the problem. So we have to neglect a little bit of air resistance in order to do that, but that's the way we're going to approach all of these problems. And so if we put a little dot here and we say that this was thrown at 5 meters per second, so I'm going to label that like the Vx, velocity in the x direction. Then when we put a dot here later in the problem, it is still 5 meters per second. And when we go here, it is still 5 meters per second. Now those are Vx's. So we assume that that stays constant throughout the problem. You want to remember that. The other thing that we can kind of look at here is, well, okay, if we're talking about it moving this way, we also see that the projectile is moving vertically as well. That velocity is not going to be constant, right? Because it's going to act like free fall. So it's going to start here from rest, and by the time it gets over here to this point, look at what it's done. It's basically fallen from here down to here. And so the velocity in the y direction, the vertical velocity, is going to increase as the problem goes on and as this thing continues to fall through the air. So those are a couple things to think about. And right away you can kind of hear probably the complexity of these, because we have to think about velocities, but now we have to say, well, are we talking about a horizontal velocity or are we talking about a vertical velocity? Because the story is much different depending on which one you're talking about. Okay, so if we were doing this live in class, I would show you a couple things. The vertical and horizontal components are independent of each other, meaning one does not dictate what the other one does. And so the famous discussion or the famous demonstration always comes from, well, what if we have like a golf ball and we drop this thing straight down? And what if we take an identical golf ball and we throw it through the air? I'm not sure my parabola is really good there. And it lands way over here. And if you noticed, I tried to draw these. I'll try to draw the ground. There we go. And if we drop this and throw this from the same height, the question is, which one hits the ground first? This one, or this one that we throw horizontally and it lands way over here? Well, the answer to this is they both hit the ground at the same time. And They both hit the ground at the same time because if you look, both fall from the same height. Gravity acts the same on both of these objects. And so gravity is going to accelerate this one down at 9.8 meters per second squared. Gravity is going to accelerate this one down at 9.8 meters per second squared. And so they hit the ground at the exact same time, even though this one's going to travel a much greater distance. Look at the path of this one. The most extreme example of this is if you have a bullet and you drop one bullet right next to the barrel of a rifle that fires a bullet out of its barrel. Even if this bullet lands a couple miles away, it will strike the ground at the exact same time as the bullet that's dropped from the same height as the barrel, which is really kind of mind-boggling when you think about this one traveling several miles, this one traveling several feet, and that's it, and they both hit the ground at the same time. That's because the X and Y components are completely separate of each other. Gravity doesn't care. That's probably a good thing to think about. Gravity doesn't care what's happening in the X direction. It is going to accelerate objects downward at the same rate no matter what. Okay, so let's bounce down. Let's get a little more technical. I guess we're probably already pretty technical here, but and look at some of these equations. Nice thing here is even though these problems are already sounding kind of involved, your equations are the same. Excuse me, they're the same from chapter 2. So horizontal equation, you've only got one. You want to solve anything in the X direction, in the horizontal direction, this is the equation you have to use. So you want to know how fast something's launched from a bow and arrow, or how fast it's thrown from somebody's hand. You're going to be solving for Vx. You want to know how far something goes, like the range of something. There's dx, distance in the X direction. And then time, how long is it in the air? That's your only choice in the horizontal direction. Vertical equations stayed the same as well. So it's the three primary motion equations that we've looked at that you guys have run a lot of problems with. So that's all good news. These are for vertical components. So how fast is something moving vertically, not horizontally? And you notice these all have the acceleration in here. And in this case, we know what the acceleration is going to be because this is vertical. The acceleration is going to be g, right? 9.8 meters per second squared. And we can put a direction on there as well, downward. So all of these accelerations will be, as long as you're on the Earth, 9.8 meters per second squared. If it's taking place on a different planet, then this would have to be given, or you'd be solving for this or that sort of thing. So those are the equations. That's kind of the run through for that. I thought we'd kind of work one problem out just to give you the feel for what these will sort of look like. So I wrote out a problem for us to solve. So let's do that. Let me grab the calculator. All right. The way I like to approach these is with a little bit of a drawing. I draw all of these. Start off with this. And because I'm not an artist, this works. And I don't have to draw anything that's in the problem, like a bridge or a cliff or a tower or any of those things. I just draw this. And I usually will put a little arrow up here. These are all going to be, remember, initially here, horizontally shot or kicked or thrown projectiles. So we can even do this if we want, draw our little parabola in there. Make this a little bit longer now. And there's our setup. And from there, I try to label stuff. So this rock is being horizontally kicked off of a bridge, and it tells us that its horizontal displacement is 45 meters. And it wants us to find I think we're missing something here. I incorrectly copied the problem. All right, so let's see. This bridge, we don't have enough information to solve it. This bridge is 321 meters. We'll just ad lib. It's all right. Everything's going to be okay. Let's look at this problem again. This rock is kicked horizontally off a bridge. The bridge is 321 meters. This is a pretty serious bridge. Horizontally, this rock travels 45.0 meters. And it wants us to find the speed at which the rock was kicked. So more stuff to interpret here. Here's Vx, right? That's the velocity in the X direction. That is the velocity given to this rock. It tells us that this thing lands 45 meters away. That is dx. So we have distance in the X direction. We now have, after I forgot it, we now have the height of the bridge. The height of the bridge is right here, 321 meters. And that we can label distance and the y direction, just to keep those separated. And so it wants us to solve Vx. We know from the equation talk that we had a couple minutes ago, there's only one way to solve Vx. That's kind of nice in the sense that we know ultimately I have to use this equation. It's the only way to get Vx. And so in terms of what we have dx, but we don't know time. And so we have two unknowns in this equation, so we can't just plug in. This one's not directly straightforward. So let's kind of label out what we do have here. We now have dy. We have dx, 45.0 meters. And I think that's all that's given in the problem. Remember, we know g. We assume this problem is taking place on the Earth. And I think that might be enough to get us started here. So we ultimately have to use this equation. We have dx. We need to find a time. And so we look through vertical equations. We kind of flip our thinking. And we say, is there a vertical equation that will allow us to solve for time? So I'm going to put our vertical equations back over here. And so you kind of think about what we have vertically speaking. And we know we've got d, right? We've got distance and we've got gravity. We also know that the thing is released from rest in the y direction. So we can kind of sort through these a little bit. And I'm thinking this is our go-to, number 2 here. Initial velocity is 0, so this will cancel. And then we've got 1/2 at squared right there as my time. So that's the winner. I'm going to use that to solve for t. I'm going to write that in down here, the shortened up version, since we know we can use that. And then I'm going to rearrange this to solve for t. And we can plug numbers in. Make sure that you put in dy here, right? We're dealing with y components. And we can solve this time out and see what we get. And I'm coming up with a time of 8.09 seconds. So this thing's going to take a little over 8 seconds to hit the ground, which makes sense. It's a pretty big bridge. This time can then be used up here to solve for Vx. So the problem gets a lot easier now that we have more information. So now we know how far it goes, dx, and we know time. We can solve for Vx. So we're just going to plug in numbers. And let's set this up. So I am getting a launch speed of, and I think everything was in 3 sig fig form. There is our launch speed, 5.56 meters per second to get that thing out 45 meters. So hopefully that gives you a little bit of a feel how you're going to kind of use some of these equations in combination to solve. You'll see this pretty common, like maybe starting with this equation and having to go get a variable to plug in, or maybe you have to solve for time here to come down here and solve for like dy. There's lots of different combinations, but expect to use a couple equations in a lot of these problems.